So for this session, we'll be doing improper integrals. So before that, let us recall the following. So we recall the fundamental theorem of calculus. Okay. So in here, the fundamental theorem of calculus says, particularly our second statement, okay, if f is continuous on the closed interval AB, then for any antiderivative capital F of small f on the interval AB, the integral of f of x dx from a to b, okay, so that's the definite integral of f of x dx from a to b, this is equal to capital F of b minus capital F of a. Okay. Now we look at the assumptions here. So our assumptions is that or are, first, we have the interval AB and we assume that it is closed and bounded interval. Okay? So it's a closed and bounded interval. And then another assumption is that the function f must be continuous on the interval AB. Okay? So continuous on the interval AB, including the endpoints. Okay? So that's the fundamental theorem of calculus. Okay? But what if the assumptions above, at least one of the assumptions above, is not satisfied? Okay? For example, what if the interval that we are considering, it's not closed or it's not bounded? We have half open or open interval. Or we include infinite intervals, say from positive a to plus infinity, or from negative a to some number b, or maybe the interval from negative infinity to plus infinity. So what about that? Or maybe what if the function is not actually continuous on the interval? Okay? So the question is, how are we going to do some integrals that is like that? Okay? Or is the integral, or does the integral exist if we have those cases? Okay? So if those cases arise, then what we have is called improper integrals. Okay? So we will discuss in this lecture improper integrals. So let us start with these improper integrals. Let us consider, okay, the region bounded by the graph of y equals 1 over x squared, and below by the x-axis over the interval AB. Okay, so this is the graph of your y equals 1 over x squared. Okay, and then we have this region. We have this region here. Okay, and then we just let A, which is equal to A of B, okay, be the area of the region. Okay, so this area here, it's just the definite integral of dx over x squared from 1 up to b. Okay, this is definite integral because we just have a closed interval here, and the function we are considering is actually continuous on this interval 1 comma b. Okay, so what we're going to do is the following. Okay, well, by fundamental theorem of calculus, okay, by fundamental of theorem of calculus, since this is continuous and we have a closed interval, then this integral here will just be 1 minus 1 over b. Okay, you can do your techniques of integration, okay, in order to solve this guy here, and you will end up with this 1 minus 1 over b. Okay, so what we're going to do is to replace this b with different numbers. For example, let's have b equals 2. Okay, then the area here, it's just equal to 1/2. Okay, That's just 1 minus 1 over 2, and that's just 1 over 2. So we have this 1/2. If we have, say, b equals 3, then you will have area equals 2/3. 1 minus 1 over 3, that's 2 over 3. Or maybe we have b equals 4, and we will get the area 3/4. Okay? And then we can replace b with any number from 1 to plus infinity. We can choose any number. Okay? So in here, if you look at this, we have the integral. Okay? We have the integral of dx over x squared from 1 up to b, and that's equal to 1 minus 1 over b. Okay? Take note, you have to integrate this. If you integrate this, okay, what is the integral? If you integrate this, okay, the integral of 1 over x squared dx, this is negative 1 over x plus the arbitrary constancy. Okay? It's not 1 over x squared, it's not negative 1 over x squared, etc. It's just negative 1 over x. So if we evaluate the integral from 1 up to b of 1 over x squared, so let me write it as dx in here, and then dx over x squared. This is negative 1 over x evaluated from 1 up to b. So this is equal to negative 1 over b minus negative 1 over 1. And that is this guy here. Okay? So what we're going to do is we let b increase without bound. So we push this b towards that. So we will put our b here, and therefore the region will include this. Okay? If we put our b here, the region will include this. And we let this b to go to some large number, very, 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 very large number. And the question is, will we still get um, an answer to this? Okay? Okay? In fact, if we do that, this is what we're going to get. If you, this guy here, the region here, it will continue. Okay? The region here, it will continue towards that. Okay? But remember, our integral from 1 up to b, okay? 1 up to b of dx over x squared, we calculated this to be 1 minus 1 over b. And now our b from here, what we did was to move it, to increase it, going to plus infinity. Okay? So I hope you're now getting the idea what will happen here. To what will happen here. We are getting the limit as b approaches plus infinity, okay, of the integral from 1 up to b dx over x squared. And therefore, this is just equal to the limit as b approaches plus infinity of 1 minus 1 over b. And as b approaches infinity, 1 over b will just go to 0. And therefore, this is just equal to 1. Okay? And therefore, the region, okay, the region here will have an area equal to 1. Okay? So what we actually did here was to do improper integration or improper integrals. Okay? So there are two types of improper integral. And the two types will be coming from the assumptions here. Closed and bounded interval, continuity of the function. Okay? So for the first type, we will try to consider this assumption. Okay? And we don't want this assumption to be true. You look at this, bounded. But in here, what we were considering is an unbounded interval. Okay? What we actually considered here, it's the interval from A to plus infinity. This is unbounded. Okay? So that is the first type of our improper integrals. Okay? So unbounded or infinite domain. So suppose the function f is integrable on some interval a comma t. Take note of this. This is a closed interval. Okay? For all t greater than or equal to a. So you have the fixed number a, you choose t. Fix that t. That will be your closed interval. Okay? So for example, if you have this number line here, this is your a, maybe you can choose your t here. So this is your interval. Okay? Or maybe you can choose another t somewhere here. Then this is the interval. Or maybe you can choose another t that lies somewhere here. Then you will have another interval. Okay? So all throughout, you will have closed interval, whatever t you choose. Okay? But the actual assumption is we assume that our function f is integrable on that closed interval, which means we can do the limit of the Riemann sum. Not necessarily the fundamental theorem of calculus, okay? Because in here, we are not assuming that the function f is continuous or not. What our assumption states is the function is integrable on the closed interval AB. Okay? So for this case, we define this integral here, this improper integral here. So the improper integral of f of x dx from a up to plus infinity in here, this is equal to the limit as t goes to plus infinity of the definite integral of f of x dx from a to t. Okay? So again, the improper integral of f of x dx from a to plus infinity, it's equal to the limit as t approaches infinity of the definite integral of f of x dx from a up to t. Okay? Provided that the limit exists. Okay? Provided that the limit exists here. For the second case here, okay, we now suppose f to be integrable on the interval t comma b. And then this is true for all t less than or equal to b. So this time, you have this number line. This is where your b is. You can choose your t here. So you will have the closed interval there. Or you can choose your t here. You have the closed interval here. Or t here, you will have the closed interval, etc. So suppose your f is integrable on this interval t comma b for all t less than or equal to b. Then we define this improper integral. Okay? The improper integral of f of x dx from negative infinity to b, it's equal to the limit as t approaches negative infinity of the definite integral of f of x dx from t up to b. Okay? So again, left-hand side here, we have the improper integral. This guy here, okay? This guy here, or this guy here, they are definite integrals only. But when you include this limit, you'll get some improper integral. Okay? So as a whole, this guy here is the improper integral here. Okay? So if these two guys here exist, okay? If this limit here exists or this limit here exists, we say that this improper integral or this improper integral is convergent. Okay? If they do not exist, we say that they are divergent. Okay? So again, in here, on the left-hand side, you have the improper integral. On the right-hand side, you have the limit of a definite integral. So aside from calculating the definite integral, you will also need to calculate the limit. Okay? Just like what we did in here. Okay? Just like what we did in here. We did some definite integral here. And as you can see, this is in terms of the letter b. Okay? And then after doing the definite integral, we apply here, we take the limit as b approaches infinity. And we found out that in this case, the limit is equal to 1. Okay? So, okay, in here, so corresponding limit above, so this guy here, if it exists, then the improper integral is convergent. Otherwise, okay, if the limit does not exist, it is divergent. Okay? And then we define the third one. So suppose we do the integral from negative infinity to plus infinity instead of just a to plus infinity or b or from negative infinity to b. So instead we are working on this interval, negative infinity to plus infinity. What we do is to divide it into two parts. Okay? Just choose any number. And then divide the interval into two parts from negative infinity to a. Maybe you choose the number a. So negative infinity to a, or you have that interval, and then the other part of the interval or the other side of the interval will be a to plus infinity. Okay? So the improper integral from negative infinity to plus infinity, this is, or of f of x dx, you can define this as the improper integral from negative infinity to a of f of x dx plus the improper integral from a to plus infinity of f of x dx. Okay? So we define this provided the improper integrals on the right are convergent. So just some quick notes or remarks. This integral here exists, this integral here exists, okay? Then this improper integral here also exists. Okay? If at least one of them, okay? If at least one of them is divergent, meaning the limit of the limit of the definite integral does not exist, then this will be divergent automatically. So we need both of them to converge so that this guy here, we can conclude that it is divergent. It is convergent. If at least one of them, okay, if at least one of them is divergent, then this will be divergent. Okay? questions? Let us look at this. So from the illustration, we got the integral or the improper integral from 1 up to plus infinity of 1 over x squared dx. And we saw that it was equal to 1. Okay? So in here, we have this. We started from some b here or some b here or some b here, but we let b approach infinity. Okay? Now, determine whether the integral 1 over x dx from 1 up to plus infinity is convergent or divergent. Okay? Now, listen very carefully and look at the solution. This is how you do it. Okay? This is how you do it. So, of course, you start with the integral from 1 up to plus infinity of, say, dx over x. The first step is to write the definition, meaning you have to write this limit thing. Okay? So, this improper integral here, it's the limit, okay, from as t goes to plus infinity of the integral from 1 up to t dx over x. Okay? You have to do this. You have to do this, especially in this course. Okay? If you don't, then you will receive some deductions. You will not get full marks. Okay? So from here, you have the definition part, and now you can start working on this definite integral. Okay? So you work on the definite integrals. When you got the definite integral, it will be in terms of this parameter t here, or variable t. So after doing that, you will have an expression involving t, and that's the time you get the limit. Okay? So for example, in here, this guy here, okay? This is what? We have the limit as t approaches plus infinity. That one will be ln, absolute value of x, evaluated from 1 up to t, correct? And take note, this is just a definite integral, okay? And your x, the interval will be 1 to plus infinity, or 1 to t. And t should be greater than 1 because, well, we are going to let t to approach plus infinity. So it is greater than 1. And therefore, 1 over x, the function 1 over x, it's continuous on the close interval 1 comma t, which means we can apply the fundamental theorem of calculus for this guy here. And we evaluate the definite integral. So we will have limit as t approaches plus infinity. This is ln of t, okay? ln of t minus ln of 1. Okay? Following so far? ln of 1 here, that's just 0. But whatever, we have ln of t here. Do you remember the graph of ln of t? Okay? So we have this. The graph of, say, this is your t, this is your y. So the graph of ln of t is something like this. So this is the graph of y equals ln of t. Okay? But as t approaches plus infinity, what happens to the value of ln of t? It just increases without bound. So the answer in here, this is just infinity. In fact, let's write plus infinity. And therefore, the limit does not exist. Okay? So the limit, okay, in here does not exist. And therefore, the improper integral here is divergent. So integral from 1 up to plus infinity of dx over x, this is divergent. Okay? Questions? So again, when you have an improper integral, you start with the definition. You write this. Okay? Some students don't do this. And because this is a Calculus 2 course, okay, this is the first time, technically, this should be the first time that you've learned this. You have to do this completely. Okay? So you start with the definition. Okay? Next, let us look at this. Integral from negative infinity to 0 of x e to the x dx. So again, we start with the definition. So let's write the problem here. Integral from negative infinity to 0 of x e to the x dx. By definition, so where is that? So by definition, this is equal to the limit as t goes to negative infinity of the integral from t to 0 of x e to the x dx. Okay? And then let us look at this integral here. Okay? In fact, let us just look the indefinite integral first. Okay? So let us solve. Let us solve the integral x e to the x dx. This is simply integration by parts. Okay? This is simply integration by parts. So integration by part here, we can let u, so remember liate, okay? So we have algebraic here and then exponential here. So we let our u to be x, dv be equal to e to the x. So here du, this is equal to dx. And v, this is simply e to the x. So this is just x e to the x minus integral of e to the x dx. And therefore, this is just x e to the x minus e to the x plus some constant c. Okay? But anyway, we don't need the plus c because we are doing indefinite integral here. We are doing definite integral here. So we have the limit as t approaches negative infinity, okay, of x e to the x minus e to the x evaluated from t to t to 0. So if we evaluate this, we have the limit as t approaches negative infinity. At x equals 0, this is 0 times e to the x. That's just 0. So 0 times e to the 0, that's just 0. Minus e to the 0, so we have minus 1. Minus quantity at t, we have t e to the t minus e to the t. Okay? And therefore now we let t approach negative infinity. So let us do this. So first, remember the exponential function, the graph of the exponential function. So the graph of the exponential function, it's something like this. Okay? But whatever, we need this side here. So this is your x, this is your y, okay? And this is negative infinity in here. Going to negative infinity, I mean. And this is the graph of y equals e to the x. So as t approaches negative infinity, this e to the t, okay, this e to the t will go to 0. Okay? The value of e to the t, as t goes to negative infinity, this will just go down and down and down. And you know that the function y equals e to the x, it's asymptotic to y equals 0. This guy here will go to 0. On the other hand, in here, we will have what? T will go to negative infinity. E to the negative infinity, okay, that will go to 0. This guy here will give you indeterminate form. Okay? So what we have in here, it's negative 1 minus this guy here will be just going to 0. And then we will still have this guy here, limit as t approaches negative infinity of t e to the t. But this is indeterminate form. This is of type infinity times 0. Okay? If this is indeterminate form of type infinity times 0, then maybe we can rewrite this expression, okay, such that it becomes infinity over infinity or 0 over 0. Does that ring a bell? If we have that, we can use L'Hopital's rule. Okay? So let me just write that. You have negative 1 minus the limit as t approaches negative infinity. We can bring e to the t to the denominator. And if we do that, we will have t over e to the minus t. Correct? And now this is infinity over infinity. Of course, t will go to infinity or negative infinity. E to the minus infinity, okay? So t going to negative infinity, e to the minus infinity or negative t, it will become e to the plus infinity. So this will just go up and up there, and therefore you will have going to plus infinity. That's why you have here infinity over infinity. Okay? So in here, we now apply L'Hopital's rule. Okay? And what do? We get the derivative of this. We also get the derivative of this. So we will have minus 1 minus the limit as t approaches negative infinity of 1 over negative e to the minus t. Okay? And now, the denominator will go to plus infinity or minus infinity because of this negative. The numerator is just constant. This will just go to 0. So we will have here negative 1 as the final answer. Any questions? Let's have another example here. We want to evaluate this improper integral from negative infinity to plus infinity. 1 over 1 plus x squared dx. Okay? Now, you have the interval from negative infinity to plus infinity. And in this case, what we're going to do is to chop the interval. Take note, your denominator here, it's always positive. Your numerator, it's just constant. So this guy here, this is defined from negative infinity to plus infinity. Okay? Which means, in fact, this guy here, it's continuous from negative infinity to plus infinity. Which means we can choose any number we want as our middle point. Let's just choose 0. So we first write the integral from negative infinity to plus infinity of dx over 1 plus x squared as integral from negative infinity to 0, okay, of dx over 1 plus x squared plus integral from 0 to plus infinity of dx over 1 plus x squared. Okay? And then we check the integral here. We check the integral here. If they both exist, then we will have an answer to this. If at least one of them does not exist, then this will be divergent. Okay? So let's do this. Start from here, this guy here. So let us have the limit as t approaches negative infinity of the integral from t to 0 of dx over 1 plus x squared. Then plus the limit. This time, since I have used t already in here, I'll use a different variable for the second part, for this improper integral here. Say, I'll just use s. So s going to plus infinity of the integral from 0 to plus infinity, or plus to s. And then we have dx over 1 plus x squared. Okay? Questions? Then, we evaluate the definite integrals that we see here. But dx over 1 plus x squared, if you integrate that, it's just your arctangent, correct? So in here, we'll just have limit as t approaches negative infinity. Quantity. We have the arctangent of x evaluated from t to 0. Then for the other side, it's the same, but the limit is different, or this guy here, it's different. This is still arctangent of x, and then the limits of integration will be 0 to s. Or we will have here limit as t approaches negative infinity. Arctan of 0, it's equal to 0. Okay? Arctan of 0, it's equal to 0. So I'll just write 0 here. And then we have the arctan of t. Then plus the limit as s approaches infinity. Arctan of s. Arctan of s minus 0. And now we are left to finding the values of arctan of t as t approaches negative infinity, and arctan of s as s approaches positive infinity. I hope you remember the graph of your arctangent. So the graph would look like this. So you have this guy here, and then you have here some asymptote. This is the line y equals pi over 2. And then we have another asymptote here. This is the line y equals negative pi over 2. And the graph would be something like this. So the graph of y equals arctan of x. So what does this mean? As your t, or as your x goes to negative infinity, the value of arctan will only approach negative pi over 2. So we will have a value for this. And as your x goes to plus infinity, the value of arctan of x will just go to pi over 2. So in here, we'll just have negative of negative pi over 2 plus you have pi over 2, and this is equal to pi. So this is the value of this improper integral here. Negative infinity to plus infinity of dx over 1 plus x in x squared. Okay? Questions? Another example here. For what values of p is the integral? Integral from 1 up to plus infinity of 1 over x to the p dx convergent. Okay? Let us see. in here, look at this. We have the integral. Let us just look at the integral of dx over x to the p. This guy here has two possible values. One, we have the ln of x, or absolute value of x, if p equals 1. Okay? And then if p is not equal to 1, you can write this as negative p dx. Integral of x raised to negative p dx. If p is not equal to 1, we will have here what? X raised to p, or raised to negative p plus 1 divided by 1 minus p plus arbitrary constant c. I forgot that plus c. Let me put it. So plus c. And then for the other guy, we will have, let me write it as 1. Yeah, let me just write it as x raised to negative p plus 1 divided by 1 minus p here, plus c, if p is not equal to 1. Okay? So, if we have that, we now solve integral from 1 up to plus infinity dx over x to the p. By definition, this is just the limit as t approaches plus infinity of the integral from 1 up to t of dx over x to the p. Okay? But according to this, we'll have ln absolute value of x from 1 up to t. Let me put the limit outside. So limit as t approaches negative infinity. Here, if p equals 1, and then for here, we have x raised to negative p plus 1 over 1 minus p here evaluated from 1 up to t if p is not equal to 1. Okay? Let me try to adjust this. Okay, so we can put it here. So we can manage the spaces here. So equals. And then what will happen? We have here, well, we still have the limit as t approaches plus infinity. In here, we'll just have ln of t, or ln of the absolute value of t. If p equals 1. On the other hand, for this, we have t raised to 1 minus p over 1 minus p minus. At 1, we just have 1 over 1 minus p. So if p not equal to 1. So in here, I wrote 1 minus p. It's the same as minus p plus 1. Okay? So I hope you got that easily. Okay. Now, for this part, we will divide this further into P greater than 1 and P less than 1. Okay, thank you. This should be plus infinity in here. Thank you. Okay. So like I said, we will divide this guy here into two parts, P greater than 1 and P less than 1. Okay. So let's do that. We have the limit as t approaches plus infinity. In here, we already have ln absolute value of t if p equals 1. In here, if p is less than 1, okay? So if p less than 1, we will have t raised to 1 minus p over 1 minus p minus 1 over, let me adjust this again, minus 1 over 1 minus p. And then for the other guy here, I'll write it as 1 over t raised to p minus 1 times 1 minus p, minus 1 over 1 minus p. So this is the case if p is greater than 1. Anyway, I'll continue on the next page. So what do we have? On the first case, if p equals 1, then we have the limit as t approaches plus infinity of ln of t, or ln of the absolute value of t. Okay? And this is equal to plus infinity. Okay? So you have ln of t here, t approaching plus infinity. So this will just go to plus infinity. That's when p equals 1. Okay? Next. When p less than 1, so we look at this. When p less than 1, so if p is less than 1, then we have the following. Limit as t approaches plus infinity of x raised to 1 over 1 minus p over 1 minus p. Sorry, it should be t here. Minus 1 over 1 minus p. But since p is less than 1, 1 minus p, this is positive. 1 minus something less than 1, this is positive. So this t remains in the numerator. And your variable t remains in the numerator. If it goes to plus infinity, then the numerator will just go to plus infinity. Denominator, it's just constant. Same is true with this. This is just constant. So this is just, again, plus infinity. And then if p is greater than 1, then let us go back to this. So you saw I wrote now the t on the denominator. Okay. So I'm writing it here. Then we have the limit as t approaches plus infinity of 1 over t raised to p minus 1, 1 minus p minus 1 over 1 minus p. And look at this. P greater than 1. In here you have p minus 1. P minus 1 will be positive. Therefore, the t raised to p minus 1 will remain in the denominator. So the denominator will go large. Okay? It will go to plus infinity. Then this whole fraction here will go to 0. And therefore, this is just what? The limit here. This is just negative 1 over 1 minus p. Okay? So this means when p is less than or equal to 1, this improper integral will go to plus infinity. But when p is greater than 1, this improper integral will have an answer. It's negative 1 over 1 minus p. Okay? So just to write the conclusion, therefore, um, the improper integral from from 1 to plus infinity of dx over x to the p. This is negative 1 over 1 minus p if p is greater than 1. Okay? Otherwise, the integral 1 to plus infinity of dx over x to the p is convergent. Okay? So here we have integral from 1 up to plus infinity of 1 over x to the p dx is convergent if p is greater than 1 and divergent if p is less than or equal to 1.